Okay, this video is going to be about a car going around a corner on a flat road with friction, and we'll see how this is going to work. So this is the same diagram from the last time with the road, and we're going to have a car that's going to be moving. So we need to know the speed of the car and the radius of the corner. This time the question is going to be, what coefficient of static friction will keep the car on the road? Will keep the car from sliding. Alright, the idea being that if there were no friction at all, the car would just go straight. So we need some sort of friction force to push the car towards the center of the circle. Right? That's what's meant by a centripetal force. Something's got to be providing the force to push the car towards the center. So what I'm going to do is I'm going to draw a front view of the car as if the car is coming straight at us. Right? So let's see, there's the tires and the headlights and the top part of the car, and there's the person driving the car. Right, so this car is coming towards us. If you look here, this is going around a right corner. So we want this guy coming around a right corner. He's coming towards you going on a right corner. What we need some friction force between the tires and the road, and the friction force has to push the car that way towards the center of the circle. Friction needs to go that way towards the center of the circle. If there's no friction, then the car is not going to turn that way. It'll just keep going in a straight line. Other forces we have over here, of course, are mg, and we have a normal force as well. Right, so let's just throw in some numbers so we can get this. Let's say the radius was 50 meters, and let's say the velocity is 20 meters per second. And it's going to turn out that the mass is not going to be necessary here. So whatever the mass is going to cancel out, right? Now up here I have mu s, so it's something to think about here is, I know the car is actually moving, but if you think about this spot between the tires and the road right there, we don't want that to slide. So we want it to be a static friction force, not a kinetic friction. If the car starts to slide, if it starts to move this way and starts to slide, then that's like this arrow up here, the car is not going to make it around the corner. So we need there to be static friction between the tires and the road right there. Alright, so as always, we usually like to draw a free body diagram, and that's basically it. So we have normal force, mg, and the friction force. I don't necessarily really care about the normal force and mg, other than I know that they're going to balance. Normal force is mg. As is usually the case when you're on a flat surface with no other forces in the vertical direction, these two guys are going to basically equal each other. So if I'm going to write a net force, I'm talking about the x direction here. In the x direction, I'm going to write F net equals ma. The only force I have is friction, m, and because this thing's going around a corner, I know the acceleration has to be v squared over r. That's part of the trick of doing these circular motion problems, is you always know what the acceleration is going to be. It's going to be v squared over r. Now you might not necessarily know what v is or what r is, but you can always stick v squared over r in for a. Now I just have to start substituting things here. Friction force is mu times the normal force, and that's going to be mv squared over r. Now I'm going to take this and substitute it in there. Alright, so now I get mu s times mg is mv squared over r. As we know, the masses are going to cancel. So if I solve this out, I'm going to get v is going to be, oh no, sorry, I didn't want to solve for v, I wanted to solve for mu s. Mu s is going to be v squared over r times g. Right, so this is sort of a equation of sorts that you can remember. What this says is that if you're going to go around a corner and it has a radius r, and you're going to be going this fast, you need to have a static friction coefficient of this much, or you're not going to make it around the corner. If your static friction isn't this much, then you're not going to make it around the corner. Right, so let's plug in our numbers that we had from up here. Let's say we have mu s equals, our velocity was 20 squared divided by r is 50 times g, 9.8. Notice how the units are going to cancel. That's going to give me meters squared divided by seconds squared. There's meters squared divided by seconds squared. So mu doesn't have any units. In this case, mu s is going to be 0.8. Right, so that's what you would need in order to go around the corner that fast. Now, online you can actually look up tables to find out what different coefficients of friction are. So here's a table that shows you coefficients of friction for different surfaces. And we can see, by the way, this site's called Engineering Toolbox. So you should know that there's lots of data on this site that you can use. And looking through here, I'm going to go down and I'm going to find tires. And here we go. So here's tire dry on the road. It's about 1. So it seems like that's possible. Interestingly enough, if you have a wet tire on a wet road, it's going to drop down to 0.2. So that's going to be a big difference. Now, what we can also do is we can figure out, what if mu was 0.2, how fast could you go? What if mu s is 0.2? Then what's your maximum speed? How fast can you go? Let's see. Right, so what if mu s is 0.2? Then what could your maximum possible speed be? Now all we have to do is take this equation, rearrange it a little bit to say v is square root of mu s times r times g. Now here's another sort of formula for you all. This says if you know your static coefficient of friction and you know your radius, then this is how fast you can possibly go maximum. Up to that speed, any faster you're going to start to slide out. So for our numbers, we'll do square root of 0.2 times our r, 50 meters, times g, 9.8 meters per second squared. Once again, notice the units are going to work out here. I'm going to get meters per second as my answer. And this turns out to be, I think I worked it out, 9.9 meters per second. So that's how fast you could go if the coefficient of friction dropped off. Some interesting things to notice here, right? Let's get a different color so we can note some things. So how does this number relate back to our original speed? And how does this number relate to our new number? So if my coefficient of friction drops off by a factor of 4, so my coefficient of friction dropped off by 1/4, my maximum speed, what happened there? Is that 1/4? Is 1/4 of 20 9.9? And you might be thinking, oh, it's just close to a half, but it doesn't turn out to be a half. It's because of this square root right here. Right, so, oh, geez, it did turn out to be half. Sorry about that. It's the square root of a half. So there it is right there. If I plug in the 1/4 right there, if my new mu was 1/4 of the original amount, and I square root that 1/4, then that turns out to be a half. So it's not always half, but it's always the square root value. So just because your coefficient of friction drops off by, say, a value of 1/4, I have to square root that value, which turns it into a half. All right, in the next problems, we're going to talk about roads that are banked at an angle instead of flat roads, and we'll see that that's going to be a little bit different.